configure the networks the way you want, and then start virtual machines that you attach to specific subnets within your networks, right? We saw also yesterday that the virtual machine approach, the infrastructure as a service approach, allows you to choose the operating system you want and potentially add disks, right? At least you would add the boot disk where the operating system lives, right? But you have the option also to add additional disks. And there are different types of disks, right? But typically to persist data, you can add persistent disks. Different type of persistent disk, SSDs, hard drive disks, right? But disks, nonetheless, right, and persistent disks that allow you to persist data. You can store data on disk on virtual machine. This is a completely valid solution, also depending on your use case. You might actually want, for example, again, full control over running a database solution, right? And you might want to take the infrastructure as a service approach, start a virtual machine, configure that virtual machine, install the database solution. That could be MySQL, that could be Postgres, that could be any database solution that you want, and install that database solution on that virtual machine and configure and maintain that database, right? And that database will write its data and store the data on a persistent disk. That's a perfectly valid solution. That would be more the infrastructure as a service approach. However, in many situations, depending on your needs, you might actually rather want to use a built-in solution, a managed solution for your storage, and essentially use a Google Cloud service and essentially upload your data through API calls again, right, to different solutions in Google Cloud to store your data in a managed way. And this is exactly what we'll cover here, right? We'll cover here the managed storage solution that exists in Google Cloud when you don't want to manage yourself, your database solution or your storage solution. And so we'll cover a few different services, right? We'll start with cloud storage, object storage solution on Google Cloud, typically where you store files, right? And then we'll focus a bit more on database solutions with a couple of services available for relational databases, right? Cloud SQL and Cloud Spanner, and a couple of solutions for non-relational NoSQL databases, right? File is typical use cases for those, what are their pros and limitations potentially, so you can choose the best solution that fits your needs specifically for every type of data, right? But so let's start with cloud storage, right? Cloud storage, as I mentioned, is an object storage solution, not to be confused with other type of storage that might exist, right? It's, for example, it is not a file storage. It does not expose a file system to your application, right? It does not allow your application to navigate through a file system, get handled on objects and modify those objects, right? It is not a file storage solution. It is not a block storage either, right? Where you would typically store chunks of a disks, for example, as block storage, right? This is not that type of solution. This is what we call object storage, where you can essentially store any type of data, unstructured data, or any type of data, right, in a key value per model, right? You essentially store your data as a binary, that would be the value of that key value, right? And the key, as we'll see, is essentially a URL, a unique URL that gives you access to that object, right? That's important to understand. There is no, this is not a file system, nor a block storage, right? Typical use case for cloud storage, so this is typically, for those of you who are familiar with other cloud providers, for example, this is typically similar to AWS S3, right? That's S3 storage with buckets. This is the similar approach on Google Cloud, right? This is a very versatile option, right? which allows you to store pretty much any type of data, right? And it has very wide use case, very wide utility, right, in your application, right? It allows you, for example, to store website content, all your static content, right? Any type of pictures, videos, any type of static content that you want to display on your website can be stored on cloud storage, allowing you essentially to have a very highly available and very performant serving infrastructure for your static content, and also offloading that static content from your origin servers, right, or from your virtual machine, and your virtual machine can now focus on delivering the dynamic content for your website, right? And offloading that part, a bit like, as we saw yesterday, offloading that part to cloud storage also offloads that on your VM that you can then downsize and save on costs on your VMs also, right? Typical use case for cloud storage. But essentially, as I mentioned, you can store pretty much anything on cloud storage, right? Another very typical use case is for archival solutions, right? Your logs, for example, any type of logs that are generated by your applications that for compliance or regulation you might need to store for a specific duration, right? For 5 years, for 10 years, you can store them in a very economical way in cloud storage, right? Disaster recovery, whatever configuration, data backups that you might have, virtual machine configuration that you might want to be able to restore in case of a disaster. Cloud storage is a typical solution for you to store that, that type of content, right? Obviously, then the choice of the location where you will store those disaster recovery files is of utmost importance. You want to ensure you store them in a location that will then be available in case of a disaster, right? We'll get back to this. And more generally, also another use case is whenever you want to make some type of content downloadable by some of your users, right? That could be your web application users, or you want to pass information to another of your employees, for example, right? You can use cloud storage to store that data, and so it can be downloaded at any point by whoever needs that data, right? Very versatile solution, a number of scenario solutions, but again, it is not a file system. It is not a block storage system. It is not a database, right? But it allows you to store essentially any type of binary, as long as you can represent your data as 0 and 1s, right? Binary information, you can store it in cloud storage. And so the idea with cloud storage, similar to S3, as I mentioned, is that you store it in a key value pair, right? Which is pretty different compared to a file system, right? So the approach for it in Google Cloud is, or in cloud storage, is that you will create buckets, top-level buckets, containers for your files, for your objects, and upload your objects within those buckets, right? So let me actually show you if I go to my Google Cloud Console instead. So I will show you a bit how it looks like and what are the different options that are available. Let me just go back here. All right. We'll get it. Just to show you a bit what are the different options available in cloud storage. So again, here, this is just a demo, right? This is not, this is no lab that we need to run or anything. Can go to my navigation menu again and go to cloud storage, right? And here, I will be able to see a list of my buckets. These are top-level buckets, top-level containers for storing information, for storing your objects, right? As we'll see later on, there is virtually no limit on cloud storage. You can upload petabytes of data on cloud storage, There is no maximum amount of data you can store in a given bucket. There is no maximum amount of buckets you can get in a project. Virtually no limit. The only limit that exists is that you cannot store objects that are bigger than 5 terabytes. One single object cannot be bigger than 5 terabytes. That's the only limit that exists on cloud storage, right? And you could potentially store petabytes of data all in one bucket if you want, right? Typically, you want to create different buckets to organize a bit your different type of data and provide some different characteristics, for example, for granting access to the data within a given bucket and not to others, potentially setting different configuration of those buckets, right? But this is entirely up to you. There is no actual limitation on those specifically. One thing to note also, you cannot nest buckets within each other. You cannot create a bucket within a bucket, etc. But these need to be all top-level buckets. Let's see what it looks like when we want to create a bucket. And here there are a few things to note that we'll comment. First, you need to provide a globally unique name for your bucket. And by globally unique, we mean unique across all Google Cloud customers. This needs to be a bucket name that is unique across the entire Google Cloud platform, right? So let me actually choose a very human readable name, right, for this bucket. Again, typically, this needs to be globally unique, and it will actually appear in the resulting URL that you will use to download the objects that are within that bucket. So you want to make sure you don't use any sensitive information within the name of those buckets, right? Because they might virtually be exposed to the URL, right? Once we have our bucket name, right, the next choice is the location. Where do you want to store that data? Where do you want Google Cloud and Cloud Storage to store that data? Any data that you upload to that storage bucket, right? There are a few options here. The first one is a regional solution, regional location. This means you choose one single region out of the 40 regions that we mentioned yesterday regarding Google Cloud, right? For example, that could be, let's say, Europe West 2, right, that we mentioned yesterday. And in this situation, your data will be stored in one single region, in Europe West 2 only, right? It will be replicated across the different zones automatically for you within that region, right? So at least you are already resilient to any zonal fail, right? And just by uploading your data, one copy of your data onto that bucket, it is automatically replicated under the hood across the different zones, transparently for you, right? Typical use case in this for that regional approach is when you want to have very low latency to retrieve your files, right? I will say file even though these are exactly objects, right? But most of the time you will store files, right? Again, it's not a file system, but I will mention files or objects pretty much interchangeably, right? But the idea here is that you will store that data, but it won't be replicated across regions, right? So typical use case for this is, for example, you have a data processing pipeline, right? You want to process that data on your virtual machines, for example, or on different services on Google Cloud. And those virtual machines run in a given region, for example, in Europe West 2. Typically here, you want to store that data closer to where you will actually process it, because this allows for lower latency in retrieving that data or writing to cloud storage. And it also lowers your network costs, right? Because you can, in Google Cloud, you network-wise, right? You don't pay for creating networks, or you are not charged for creating networks or creating subnets. You are charged for the network traffic that flows over Google network. So having your data closer to where it is actually needed for processing is a good option in those solutions. However, data is not replicated across regions here. If something happens, anything happens, that might be a natural disaster, as we mentioned, right? In Europe West 2, you lose access to your data. In those situations where you want still low latency, but higher availability, replication across regions, right? You might want to choose a dual region, in which case you choose a given geographical region, for example, Europe again in our case, right? And I can choose still Europe West 2 and say, okay, that data will be automatically replicated by cloud storage in Europe West 1 in Belgium, in Europe West 3 in Frankfurt, for example, right? I choose two regions. Two regions. Now, if one region goes down, I can still access my data from the other region. And this is typically, for example, something you might want to consider now if you want to store disaster recovery solutions. Because now, if you have your different resources, for example, running in Europe West 2, and you want to you have your database running in Europe West 2, in London, you have your database, your applications running there, and you want to take data backups, configuration backups, etc. for disaster recovery, you need to make sure you don't store that disaster recovery data in the same region. Because now if the entire region goes down, you would also lose access to your disaster recovery backups, right? So you want also to store that data in another region, right? This would be, for example, a scenario for that dual location, right? For that dual region approach. And in some cases, what you want is the highest availability. Highest availability, ensuring that your data is replicated across 3 regions in this case, 3 regions within a geographical area, right? And can be served from those 3 regions at the same time. And you can potentially lose even one of those regions or even 2, your data would still be available, right? When you need the highest availability, for example, to serve your static content, right? You serve static content to your users, you want ideally, right, to have that content delivered as fast as possible to all of your users. By serving that content from different regions, you can have lower latency for your end users, right? So with multi-regional, you now this time choose an entire geographical region, right? Either America, Asia, or Europe. But here in this case, as you see, you cannot choose and you cannot know across which region your data is actually replicated, right? So less control, but highest availability. Depending on the use case, you might want one solution, one replication option or another. One thing to note, in all of those solutions, either multi-regional, dual regional, or regional, right? Replication is strongly consistent, right? There is strongly consistent replication that happen between those different regions in all situations, right? This is with external strong consistency, meaning that you ensure that everybody has the same version and the same copy of the data, right? Let's choose a regional one here, right? We won't create the bucket anyway. Next option is for you to choose a storage class. Now, a storage class is essentially a metadata that applies to an object, which allows you to save on storage costs. The only purpose of a storage class is potentially for you to save on storage costs. In cloud storage, you are essentially charged for the data you store on a per gigabytes per month basis, right? Now, if you know there are some type of data, there are some type of objects you won't access that often, you can leverage storage classes to lower your costs on storage for those objects, right? Now, what we choose here is the default class. What this means, this is the default storage class metadata that applies to to the objects you upload to that bucket unless you specify otherwise. And this is also something to note. Within that bucket, even though I have chosen a given default class of standard, for example, I can at any time upload an object to that bucket specifying that I want to store it as CodeLine, right? And you can have different objects with different storage classes within the same bucket, right? You can then update those storage classes individually for those objects, right? After the fact, once they have been stored in the bucket, right? This is again just really the default class here. But essentially, depending on the access pattern you expect for the different objects, you might want to apply a different storage class. The standard one is typically for hot data, what we call for hot data, data that you know will be accessed regularly, that might be deleted pretty shortly, right? That you want to access frequently, right? This is the standard class. There is no discount on storage costs, but there is also no additional fee to retrieve that data. Now, for data that you know that will be used less than once per month, for example, that could be, or at most once per month, that could be, for example, for some data that you know that can be queried only less than one per month for some reporting capability, for example, etc., right? You might want to apply the nearline storage class. The storage cost will be lower. However, there is a retrieval fee that applies. I know, for example, by heart in the US Central 1 region, right, the one in Iowa, in the US, standard storage cost is $2 per gigabytes per month. $2 per gigabyte per month. $2 sorry. $0.02, right? 2 cents per gigabyte per month. And no retrieval fee. In Nearline, this is half the price for storage. This is 1 cent per gigabyte per month. However, there is a retrieval fee of 1 cent per gigabyte, which means that if you retrieve that data once per month, it just essentially cancels out, right? The retrieval fee cancels out the savings you have on storage, and you eventually pay the same price. And if you retrieve that data more than once per month, it will eventually actually cost you more than being in storage, right? In the standard storage class. So this is something to take into account, right? You need to ensure you know your data usage pattern, right? CodeLine is for data that should be accessed less than once per quarter. Typically, for example, for disaster recovery solution, right? Where you generally don't want to access that data too often, right? But you want also, in any case, to test your disaster recovery scenarios, right? So you want to access that data at some point, right? For example, CodeLine could be a good fit here. Or Archive is when you use your data the less, right? Less than once per year, typically for archiving of data, right? You need to store for compliance your logs for 5 years or 10 years. Archive, and you will barely access them. Archive would be a good solution, right? Where you will save the most on storage costs. But again, this is the default storage class for that bucket that will apply to the objects you upload to that bucket if you don't specify a storage class when uploading those objects, right? And note also that there is the auto class solution. The auto class essentially is a newer solution, has been around for maybe a year or two now, that essentially automatically changes the storage class of your objects depending on how often it is accessed, right? It starts with standard, right? And it can move it to the nearline storage class based on the access pattern, right? To automatically allow you to save on storage costs. But again, you can choose your own default class and have it and modify it, manage it yourself whenever you want, right? We see also that there is something that's called lifecycle management, right? These are automated tasks that you can set to apply some specific changes to those to your objects and potentially to the storage class of your objects, as we'll see later. Storage class, right? Next option that you have in cloud storage is you can specify how you want to control access to the objects within that bucket, right? The default solution and the recommended approach is to use uniform. With uniform, you rely entirely on IAM permissions, IAM roles, to grant access to users or to applications to your objects. You can apply them at the bucket level. Remember, with IAM permissions, IAM roles, you can apply them at different layers within the hierarchy, right? So you can apply them at the bucket level, meaning that, for example, let me show you here, right? If I go here to buckets, let me open it in a new tab. Here I've got my different buckets, right? And I can choose, for example, let me see, all right, for example, one of those buckets, right, this bucket specifically, I can select that bucket and go to edit access. And here I can grant access to a service account, a user account, right? Essentially as we did yesterday with IAM, right? That could be any user, any service account that could be granted IAM permissions. And at this point, I could go and, for example, choose the storage object viewer role, right? Storage object viewer, that means the identity that is granted that role can view the object, can download. This means that it cannot create or delete objects within that bucket, but it can view all the objects within that bucket. And that's the important aspect here. That role applies to all the objects within the bucket. You just grant access at the bucket level. I can potentially grant that access at the project level, which means that would apply to all the buckets within that project or even higher up in the hierarchy, right, at folder organization level. But this is what we call the uniform because it applies to all the objects within that bucket identically. This is the recommended approach because it makes things much easier to manage, right? But in some cases, you might need to have a finer grain control onto who can access which objects within a given bucket. Here you can use, for these situations, you can use the fine-grained approach, which allows you to use on top of IAM, because IAM roles still apply, right? At the bucket level, at the project level, etc. But now on a per object basis, you can use ACL's access control list to essentially specify who can see what on those objects, right? For example, that bucket, let me see, that bucket here, right, is of type uniform. I could not go and grant access to individual objects, right? It only applies to the whole bucket. But this bucket has fine grain. So now at this point, I can go onto individual objects, right? Edit access to that object and grant a specific user, a specific role, owner, reader, writer, etc., right? Access control list on a per object basis. But again, typically, unless strictly necessary, the best approach is to use uniform. It makes things much easier to manage on the long run, right? And essentially, this is cloud storage and cloud storage buckets, right? There are a number of additional capabilities that you can set. A newer capability that was introduced a few months ago is the ability to set a delete delay, right? So whenever some user, whoever requests an object to be deleted, you can force that object to be kind of cached, right? Or kind of put in the trash, right? So it appears as deleted, but is soft deleted and won't be definitely deleted until 7 days, for example, in this case, right? allowing you to potentially restore that data within those 7 days, just to ensure you don't delete data by mistake, right? With one thing to note, you will still pay for the storage of that data for the 7 days that it is soft deleted, right? But that can be useful. Another thing to note is, and that comes from an important fact, objects in cloud storage are immutable. Again, they are not files, right? This is not a file storage where you can access a file, get a handle on the file, a lock on the file, and update that file in place, right? This is an object storage, so if you want to modify an object, you need to download it, modify it locally, and re-upload it. But when you re-upload your modified object, under the hood, it effectively replaces the previous version, right? If you want to keep those previous versions for history, to get history or to be able to roll back to previous versions, etc., you need to enable object versioning. You can then choose how many versions do you want to keep. You can have a lifecycle management policy to automatically delete the oldest version and only keep the 3 most recent versions, for example, etc. Right? But this is an option. And lastly, you can even let me show you. And lastly, you can set retention. Remember, I mentioned earlier that you can, for example, for compliance, say, all right, I need for compliance to store my my logs or specific type of data for 5 years. And you want to ensure that data cannot be deleted or cannot be modified for that amount of time to be compliant, right? So here you can set, for example, bucket retention policy and specify, all right, data in this bucket cannot be modified or deleted in the next 5 years, right? So this is, these are the different options. And last thing I will mention, this is interesting and about what we mentioned yesterday about one of the security aspects that Google takes, right? Data, as you see here, is encrypted. Data is always encrypted. This cannot be disabled. You cannot disable encryption key, as you mentioned, as we see, right? The only thing you can do is get involved into managing the encryption key. By default, Google manages the encryption key. But you can yourself manage the encryption key yourself with KMS, right? Key management service on Google Cloud if you want. You can generate keys software-based or hardware-based, right? With hardware security module. You can even use your own key, right? Not from the UI, you can actually do it from command line. You can even generate your own key pair, for example, with your tool of choice and specify your public key to encrypt data, for Google to encrypt data. And only you with your private key will be able to decrypt that data, right? But data is always encrypted, and this cannot be disabled. I show this here for cloud storage, but this is actually also true for every storage solution that we'll see in this module, right? Because again, as we mentioned yesterday, everything is encrypted in, every customer data is encrypted in Google Cloud, right? So this is cloud storage. Very, one of the most widely used services in Google Cloud, right? We've covered this, right? Remember, objects are immutable, but you can enable object versioning to keep history of those versions, potentially then decide to serve by default the version 2 of that object. You can even delete previous object, roll back to other versions, etc., right? Object versioning. Access control, this is what we mentioned. Either uniform, where you use only IAM at the bucket level, and this applies to all objects similarly, right? Or fine-grained solution where you use ACLs, access control lists, where you can set different access on a per object basis. One thing to note also, we mentioned cloud storage is not a file system, right? It is an object storage solution that can out of the box, that cannot be mounted as a storage file system on your machines, right? On your local machine or specific machine. You do have a number of tools, a set of tools in Google Cloud, for example, that is called GCS Fuse, right? Google Cloud Storage Fuse, that allow you to emulate a file system from a cloud storage bucket. That is a tool and of an agent you run on your machine that emulates a file system for your operating system, right? So from your operating system perspective, it writes to a file system, but this is under the hood translated to uploading and downloading objects to a cloud storage bucket, right? This is something to consider, right? In case you might want to emulate that capability, right? Even though you need to be aware also of every access for your object is actually a download of that object, right? So this might also be chargeable, etc. Right? The lifecycle management policy tool that I mentioned earlier, right, which is essentially a kind of a task, right, a recurrent task that you can configure to apply changes based on some conditions on your objects. You can, for example, set a lifecycle management policy on your bucket to say, all right, I want objects older than a year to be automatically deleted. And regularly, it will check if there are objects older than a year and remove those and delete those if needed, right? With specific dates, you can choose to keep only the 3 most recent versions, or you can potentially automatically change the storage class, right? And for example, say, all right, if an object is older than 3 months, change its storage class to another storage class, etc. Those are the different storage classes that we mentioned, right? Standard, nearline, code line, and archive, each with their expected access pattern, right? As I mentioned, less than once per month, less than once per quarter, or less than once per year. However, again, as I mentioned, this is only metadata applied to your object, right? It does not change anything else related to your object. It does not move your object to other buckets. They stay in the same bucket, in the same region, in the same location, right? Your objects are still replicated if they are stored in a multi-regional bucket or dual regional bucket, right? And you access those objects in the exact same way, through the exact same API call, etc. Right? There is no change in that object in any way. The auto class that we mentioned for StoreNet, right, for storage class, that can automatically be changed, as we mentioned, right? And as we mentioned, automatic encryption of your data, no need for provisioning of capacity, fully serverless solution, you just upload your data, right? You can just upload your data, and cloud storage takes care of scaling for capacity for you to store that data, right? And you only pay for what you use. You pay for the storage of your data and potentially retrieval fees if you use a non-standard storage class, right? Now to finish a bit with cloud storage, when it comes to uploading data, right? We mentioned that no prior provisioning of capacity is actually needed, right? You can upload your data the way you want. Now there are different ways to upload your data depending a bit on the amount of data you need to store and potentially your available bandwidth on your local machine or your machines from where you want to upload that data, right? One option is online transfer. Online transfer can be done through the Cloud Console, through the CLI command, right? You upload your data from your machine, from where the data is stored at this point, and you upload it to cloud storage, right? Another option is to use the serverless storage transfer service in Google Cloud. This allows you to set either one-off, on-demand, or recurring transfers for data that you might want to move from one bucket to another, for example, right? And say, all right, move or synchronize a bucket with another bucket on a per week basis, for example, etc. but quite importantly, also allows you to set jobs to transfer data from remote locations to cloud storage. That could be, for example, an endpoint on your on-prem where you expose data and you want to store it on cloud storage. That could be from AWS S3. You can specify a storage transfer service job, either one time or recurring, to synchronize an S3 bucket to a cloud storage bucket. Pretty convenient too. And lastly, and this is typically in the case where you have a huge amount of data. Imagine you have potentially hundreds of terabytes of data that you would want to upload to cloud storage. Depending on the bandwidth you have available within your organization or from your machine, this can potentially take substantial amount of time, right? Ages, potentially days or weeks, depending on your bandwidth. Another option is to use transfer appliance and get a rack of storage disk and storage capability shipped to your location. You can then encrypt your data, upload it to that rack, and ship that rack back to Google Cloud, and Google Cloud will upload that data to cloud storage, right? For a huge amount of data that you don't want to transfer over the wire, etc., this would be the solution for you. But once that data is on cloud storage, it is accessible from pretty much anywhere, right? Depending, obviously, if you have the necessary permissions to access that data, right? But you can integrate it with BigQuery. You can query the data in cloud storage with BigQuery. You can access it from your applications running on VMs, on App Engine, pretty much anywhere, right? So this is cloud storage, the de facto solution for you to store most of your static content, files, disaster recovery, archival solution on Google Cloud, right? For unstructured data, now we move to the database solutions. Now, when it comes to storing data into databases, right, depending a bit, again, on the type of data that you want to store, you want to store structured data, unstructured, semi-structured data, etc., right, you need different database capabilities, right? So we'll focus first on the relational database solutions, and we'll start with Cloud SQL. Cloud SQL is essentially a managed service to run either a MySQL database, a Postgres database, or a SQL Server, Microsoft SQL Server database, right? Similar to, for example, again, AWS, just to give you a quick idea, similar to RDS, for example, in AWS, right? Where you can run managed, you can use managed services to run well-known solutions, right? Again, another option for you would be to create a virtual machine, configure the virtual machine, apply dependencies, install the MySQL or Postgres database software, configure the software. You would then typically need to configure the network also, so that this database, this virtual machine running that database, is accessible by other application that needs to send query to that database. You typically would need to, if you want higher availability, you would need to set up and configure an entirely new virtual machine with, again, the same database software, configure replication, configure automatic failover capability. You might need to, you still want to configure backups, regular backups, ensure they are stored in a secure way. You want to potentially create other virtual machines to, with, again, a replica of that database to provide read replicas, etc., right? Pretty tedious process, right? That is done entirely for you with Cloud SQL. Google Cloud and Cloud SQL takes care of everything, of setting up the VM, setting up the replication, setting up failover, setting up backups, managing those backups for you, updating your database software whenever there are new versions automatically for you, right? So this is managed solution for either MySQL, Postgres, or Microsoft SQL Server solution, right? Just to show you a bit what it looks like, if I go to my project again and I go to SQL, right? And let's say I want to create an instance. Create instance, and here again, we can see I can choose either MySQL, Postgres, or SQL Server. Let's choose Postgres, for example. There are a few options that you can choose, right? A few profiles, depending a bit, but importantly enough, you can essentially just choose the version of Postgres you want to use, right? You choose the name of the instance, a password to access your data, the region you want to run that Cloud SQL instance, and this is an important aspect because under the hood, this is essentially, in this case, one machine, one VM, right? One virtual machine, if you run it in a single zone, obviously not recommended in production, right? Because there is no failover. If something happens to that VM or something happens to that zone, you lose access to your data. But that's an option you can choose, right? You can choose multiple zone, and now you would have two instances. Obviously, this is more expensive, right? But now you have another instance that is automatically created in another zone, right? And replicate the data from the primary instance. And if something happens to that primary instance or the zone where that primary instance runs, it takes over automatically, right? But in both cases, both instances, they run in the same zone, in the same region, sorry, right? In the same region. So you need to choose a given region to run your database solution. But at this point, that's pretty much it. I could create an instance at this point, and it would use that default configuration that we see here, right? Default of 200 gigabyte storage, 8 CPUs, 32 gigs of memory, right? And a number of performance capabilities, right? You can then, if you want, customize those options, right? Provide more or less CPU and memory, for example, to support more concurrent connections. You can specify different type of connections with external IP, internal IP if you want, different configuration options, but everything under the hood is managed for you, right? Kind of the platform as a service solution for your database instead of having to run it yourself and configure it yourself. Very convenient way to store data, right? The typical use case, for example, is when you run a Postgres or MySQL database or Microsoft SQL Server database in your on-prem, you can typically move that data as is into that solution, right? Into a managed solution instead of running a lift and shift and actually having to run your virtual machine yourself in Compute Engine, right? But automatic backups, automatic replication of the data, etc., right? Very convenient solution, right? From which you can then access data from pretty much anywhere, depending a bit on the configuration you specify. Do you specify an external IP? Do you specify only an internal IP that you want to connect to one of your VPC networks, right? But very easy integration with other solutions. As long as, remember, your application's service account have the necessary permissions, IAM permissions, also remember the Cloud SQL client role from yesterday, for example, to access Cloud SQL, right? But for the rest, these are pretty standard solutions, right? So you can use your tools of choice, Workbench, to actually interact with those databases solutions as you would do normally, right? Now there are a couple of, I would say, limitations with, depending on your scenario, depending on your use case, there are a couple of limitations, I would say, with Cloud SQL, right? The first one is that you can store only up to 64 terabytes of data per instance. That's already quite a lot of data, but in some cases, you might want to store more than 64 terabytes of data on one single instance. And the other limitation is that it is a regional solution. It is a regional option, meaning that it can live only in one single region. Again, you can create a failover replica, you can create read replicas, but generally in the same region. Depending on your scenario, that might suit you on it, right? If you typically have a regional user base that you expect to query data from closer to that region, right? But in some cases, you might actually have a worldwide user base, right? And typically this means that they will experience higher latency just for the mere fact that they query that data from far, right? Let me actually just illustrate this quickly with a quick tool. GCPing, don't remember if it's gcping.com. Yes, it is. What this essentially does, it is a bit slow. It used to be a bit faster, but it's a bit slow to start at this point. But what this tool does, it essentially sends a request from my local machine. I'm myself located in Barcelona, in Spain, right? And it sends a request to all the available Google Cloud regions across the globe, right? And it essentially returns the latency for those from those particular data centers, right? So again, it takes some time for that latency to come up, right? But what we see is at some point we should see Madrid actually come a bit above, right? But what we see is the closer the regions are, the faster we get a response. That makes sense, right? That just that round trip for that network connection, right? So for example, we are talking about just a few dozens milliseconds if I need to query to Belgium, to Germany, etc. Right? But if I needed to query data that was stored in a Cloud SQL database running in an Indian region, for example, right? I would take already almost 400 milliseconds just for that round trip. Plus, at this point, the time needed by the database to process the query and return the result, right? Could potentially take half a second or a second just for the mere fact, right? Just for the mere distance. While when it's closer to me, right, I will get that data much faster. So for applications that are latency critical, right, for which latency is very important, right, or for applications where you want higher availability, you would want that data to be replicated across regions, so then you are even resilient to a regional failure, right? If something happens to that region, you still have access to that data. For those solutions, more than 64 terabytes of data and replicated data across regions, the solution of choice in Google Cloud is Cloud Spanner. Now, Cloud Spanner is really the Rolls-Royce of relational databases solutions on Google Cloud, right? It is a highly scalable solution that essentially scales horizontally, right? It now stores data on an underlying Google proprietary file system, right? And essentially you provision a number of nodes to query that data and serve that data, right? And the more nodes you provision, the more data you can store, up to petabytes of data, and the more concurrent requests it can serve, right? Making it much more, making it horizontally scalable. You add or remove nodes as you need, right? Making that solution highly performant and that performance at a huge scale, right? Just to give an idea, last year, Google finished migrating all the Gmail data, trillions of emails, information, they migrated those from Bigtable to Spanner. So Spanner is now the storage solution that powers many of Google Cloud services, including Gmail, right? To give you an idea a bit at which scale this can actually operate, right? And the other aspect, very powerful aspect of Cloud Spanner is that you can have it replicate your data automatically across different regions. You can choose to have your a cloud storage, a Cloud Spanner solution, storing your data in one single region. That's an option. You still can store petabytes of data in that region and not only 64 terabytes like with Cloud SQL, right? But again, that would be in one single region. No replication, not that latency advantages we mentioned earlier. But you can also configure it by just a tick of a button to replicate data across several regions. There is a solution, for example, there is an option, there is a profile to have your data automatically replicated across 2 regions in North America, 2 regions in Europe, and 2 regions in Asia. And your data, whenever data is uploaded to cloud storage, to Cloud Spanner, sorry, data is automatically replicated across all of those regions with strong external consistency. The Rolls-Royce of storage solutions on Google Cloud, right? With much higher availability, typically, because now even if you run a regional Cloud Spanner, data is automatically replicated across the different zones. If you run a multi-regional Cloud Spanner, data is replicated across different zones, across different regions, even resilient to an entire regional failure, right? Making it much more available, right? Just to give an idea, it reaches 5 nines availability SLA for multi-regional replication and 4 nines for regional Cloud Spanner, right? But 5 nines for a multi-regional deployment, right? Which is less than 5 minutes downtime, possible downtime per year. Very highly available solution on Google Cloud with strong global consistency for that replication. And again, remember a scaling amount of data you can store and amount of reads and writes that it can support based on the number of nodes you provision. But again, here, this is not now a serverless solution. Cloud storage is a serverless solution. Cloud SQL is not, because again, you choose how many instances you want. Cloud Spanner is not serverless either because you choose the number of nodes you want to store data and to retrieve data. So these are the solutions for relational database, right? Relational database on Google Cloud. Now, what about NoSQL database, right? For your semi-structured data that you might want to store on Google Cloud. In Google Cloud, there are two solutions for it, right? Depending again on your use case, you might want to consider one or another. The first one, Firestore. Firestore is a fully serverless solution. You just upload your data, it takes care of the rest, right? It scales horizontally under the hood, right? But that's entirely transparent for you. You essentially upload your data, it takes care of the rest. And it provides a data model based on documents and collections. You create your data as a document with a number of fields that apply to that particular type of data, right? And again, you can store many different types of data. There is no strict schema. This is a NoSQL database, right? And you can then organize those documents into collections. And you can then query that data, retrieve individual documents, retrieve all the documents within a collection. Essentially, it relies on indexing of your queries, right? This is an indexed database solution that has hence a bit more limited querying capabilities, right, than a full SQL solution where you can use joins, where you can have pretty powerful capability, right? Now it needs to have an index to retrieve the data. Now it means also that it has blazing fast performance, right? Because every query that it runs can get that data from an index, allowing it essentially to scale very efficiently, because now it scales based on the result set, on the size of the result set, and not of the entire data set it runs the query against, right? Because again, the queries are indexed, right? So pretty powerful solution, right? That you would typically use for web application, to store data for your web application, for your mobile application, etc. Right? Typically in the range of a few dozen terabytes, typically, right? And it is very well suited for web application or mobile application, more specifically even because it does provide a set of client libraries that provide additional capability out of the box for you, right? With, for example, online synchronization. This means that you do have a client application that updates data to your database. Other client applications that are listening to those changes can be automatically notified and updated. It supports offline data synchronization, meaning you have a client application that wants to update data to the database, but it has flaky network connection, flaky internet connection, and it does not have network access at this point. Those updates, those changes to the data will be cached within the client application thanks to the client library, and those changes will be automatically applied whenever the network connectivity comes back, right? A number of solutions and tools that make it very suitable for storing data for your web application, mobile applications, etc. Right? Very powerful solution, fully serverless solution, as we mentioned, and that does also have the ability, as with Cloud Spanner, to replicate your data across multiple regions. You can again have a Firestore database running in a single region or in a multi-region aspect, right? With again 5 nines availability for multi-regional deployment and 4 nines availability SLA for regional deployments, right? But again, data replicated across those different regions with strong consistency. Very powerful solution with one thing to note, however. With cloud storage, with Cloud Firestore, right? With Cloud Firestore, you are charged for the storage of the data on a per gigabyte per month basis. But you are also charged for actions that you take on that data. You want to read data, to write data, to delete data. Those operations are also charged. There is a free tier for a number of free operations you can apply per day to your data, but past that free tier, you are actually charged for operations you apply to that data, which for applications or solutions where you expect a very high and huge amount of reads and writes to your data, this can get your cost rise significantly, which make this solution not exactly suitable, for example, for storing data for data analytics, right? Where you might have thousands, tens of thousands of IoT devices that need to write data to a database and a machine learning pipeline that constantly queries that data for analysis. You will incur quite a number of costs for those retrievals, right? So for this use case, you would typically rely on Cloud Bigtable, which is the last solution we'll cover for today, right? Cloud Bigtable solution, which is arguably the weirdest solution, storage solution on Google Cloud, right? But is designed has been designed, I believe it's around since 2004 in Google, if I'm not mistaken, that handles massive workloads, huge amount of reads and writes, low latency, consistent low latency, up to single-digit millisecond latency for the same region retrieval, right? High throughput, typically for high demanding workloads, for analytics, for when you want to store time series from your IoTs, for example, etc., right? Very powerful solution that allows you to store petabytes of data. Petabytes of data that you can then query, read and write with huge amounts of concurrent connections and high amounts of operations and reads and writes, right, for your data. Typically to run machine learning algorithm on the data, etc. But now you are not charged for the individual reads and writes, right? You are charged for the number of nodes you apply. So similar to Cloud Spanner, you provision a number of nodes to provide capacity. And the more nodes you add, the more throughput it gives you, right? Throughput scales linearly with the number of nodes you add. Depending on your needs, you will provision one more or less nodes, right? But for the rest, Bigtable also exposes, and this is something interesting to note, you can stream data into cloud storage, you can load batch data into cloud storage, and you can query that data using the HBase ecosystem. So if you have already applications relying on the HBase ecosystem to query data into your existing databases solutions, you can store your data in Cloud Bigtable and still have that data available with minimal changes to your application, right? Again, that portability that we mentioned earlier. And lastly, just to finish also on this, right? BigQuery, we won't cover more details about BigQuery specifically, but just so it's not confused with Bigtable, right? BigQuery and Bigtable are completely different products. Bigtable is what, as we mentioned just in the last few slides, a NoSQL storage solution. For semi-structured data, a NoSQL database solution that is meant to store data, to serve it to other applications, right? BigQuery, on the other hand, is a data warehouse solution. You can store data in BigQuery, but the purpose of that data is to be analyzed in place using the querying layer capability of BigQuery, not to serve that data to other applications. Not that it cannot, right? Not that other applications cannot get data from BigQuery, but it is not meant for it. It is not optimized for it, right? It is not a database solution. It is a data warehouse solution where you store data for analytics, for analysis in place in BigQuery, right? Essentially, these are the different solutions available to you in Google Cloud for managed storage capability, right? With, again, different use cases for each of those. We'll just do a quick recap and we'll go to our 10-minute break just shortly after, and then I will actually run the lab after the break. It's going to be easier that way, right? But essentially, just as a quick recap, cloud storage, remember, unstructured data, any type of file, any type of static content, disaster recovery, backups, archiving, etc., right? Where you can store petabytes of data and virtually no limits except that 5 terabytes per object. For the rest, no limit on cloud storage, fully serverless solution. Now for SQL, now for relational data and SQL databases, 2 options. Cloud SQL, the managed service for MySQL, typical solution for running a database solution in a managed way, right? With a couple of limitations, as we mentioned, up to 64 terabytes of data only, right? And the regional the regional aspects, right? It can live only in one region, potentially with several replicas, right? But this is typically a regional resource. For higher needs, right? Either you need to store more than 64 terabytes of data, or you need that multi-regional replication. Cloud Spanner is the solution for it on Google Cloud, right? Huge scale, massive scalability, again, the Rolls-Royce of relational databases, as we mentioned, right? Where you can store up to petabytes of data. And for NoSQL databases, as we mentioned, right? Firestore, fully serverless solution that automatically scales with your data, where you typically store in the range of terabytes of data, terabytes, a few dozens of terabytes, where you typically store data for mobile applications or web application, right? But remember, you are charged for storage and for operations that you apply on that data. So typically for use cases where you expect to store petabytes, up to petabytes of data and huge amounts of reads and writes of your data, on your data, Bigtable would be the solution of choice, right? Where it does allow you to store petabytes of data, essentially in one single Bigtable organized. There are a few things to take into consideration for performance, right? How you design your keys for your data, right? I won't get into too much detail, but pretty interesting. Very powerful solution here, which is not serverless again, as we mentioned, right? You need to provision a number of nodes. And here, just to as a note here, it mentioned does not support SQL queries because that's a NoSQL database, right? However, if I'm not mistaken, I verified this the other day. Google Cloud Bigtable SQL support. Bigtable now supports SQL queries, right? Just to as a side note on this, right? So you don't rely on that information here specifically, right? Bigtable does support SQL queries now. Feel free to have a look at the blog, right? If you type Google Cloud Bigtable SQL support, you will have access to that documentation. All right. So storage solutions in Google Cloud. Again, a wide variety of solutions for you, depending on your needs, depending on the access pattern, depending on the type of data you need to store. Quite a number of solutions in Google Cloud, right? And we'll be able to run the lab. So again, I will showcase the lab. I will run the lab myself, just so you see a bit what you will need to do, etc. Right? We'll use actually cloud storage and cloud SQL. But I will enable the lab for you all at the end of this session, right? But before we run the lab, let's have a short 10-minute break, right? So you can rest a bit and get ready before we get to that lab demo, right? So let me do as we did yesterday and set a 10-minute countdown timer on screen. So we are all on the same page. And we can all come back in 10 minutes to jump into the lab, right? So enjoy your break and see you in 10 minutes. Let's start the timer. See you in 10 minutes. right? 1 minute left until we finish our break. We'll continue shortly then with the lab. All right. So we are back after our short 10-minute break for this first break for today, right? And so as I mentioned earlier, we'll be able to jump right into the lab that we have for this section. So again, I will actually run the lab myself just to show you a bit what is required in the lab, what a few different details, right? So you can keep it in mind. But the lab for you, for all of you, won't be enabled until the end of this session, right? Same than yesterday, I will enable the remaining 2 labs at the end of this session, so you will be able to run those labs right after the session, right? But I'll go over the lab myself so you can see a bit what it takes to run this one, right? So let me actually bring it again on my side here. Let me close this here. And so at this point, right, I can actually open the lab. Again, I can do it, right, but this is not enabled for you. You should still see something like this, right, with those 2 labs currently disabled. This is expected. I will enable them at the end of this session. But once they are enabled, you will need to run those 2 labs, right? So same idea than we did yesterday. To start the lab, we click on Start Lab button. We see we have 1 hour and 15 minutes here, right? Should not need that, that amount of time. You might see, generally when you start the lab, resources are readily available, right? You might see this message. It just takes just a minute or less to provision the resources, and that's done, right? So we are done already. And so again, we do have a new project ID, and a new set of username and password. So same idea than we did for the previous lab. We open an incognito window to be able to log into the Cloud Console with the username and password that are given to us. Let me organize this a bit better here. All right. Let me just close that. Perfect. And here I will actually just scale it down a bit so we can see a bit better. And we are in, right? So again, we understand something. We agree to a few others, right? Same idea as your student account, so don't worry, no, nothing related to your own account. And remember to verify that you are indeed using the correct project, right? So this should be the Quick Labs project provided for the lab itself, right? And verify also that you are logged in with the student account. And at this point, we are in the Google Cloud Console already, so we are able to start with the lab. Now, with this lab, we will actually run a very simple web application. You will see the goal for it is not to make a beautiful or fancy web application. It is really basic, but it will illustrate connectivity with cloud storage and Cloud SQL, right? So we'll essentially install a web server with PHP, web development environment, etc., right? And create cloud storage buckets and a Cloud SQL database, right? So we see the different steps here, right? We create a cloud storage bucket, and we place an image into that cloud storage bucket that we will be able to retrieve from our web application running on a compute VM, right? We create a Cloud SQL instance and configure it. We connect to that Cloud SQL instance from our Compute Engine instance and the web server running on that Compute Engine instance, right? And we also use the image running in cloud storage, right? So here, same idea. Task 1, sign into the Google Cloud Console. This is what we've done already. No need to do anything else. So we could start, and I would typically recommend you to start with task 2, right? But what we see here is task 2, we deploy a web server VM instance. So we deploy the VM instance and we configure the web server, right? Then we create a cloud storage bucket to store that image. And then we create the Cloud SQL instance to be able to run our database, right? Just for the sake of this demo, I will actually start with that task 4 first, right? Because I know Cloud SQL takes quite some time to create a Cloud SQL instance, right? It can take anywhere from 5 to 10 minutes. So I will perform those tasks first and then come back to the beginning, right? But in your case, you can actually run them in order. There is no problem with it, right? So first, in the Google Cloud Console, let's navigate to Cloud SQL. So we go to Cloud SQL, click Create Instance. We close all that, dismiss, Create Instance. Choose the database engine, select, choose MySQL. So we'll choose MySQL. We want in the Cloud SQL edition to click on Enterprise, right? And select Sandbox from the drop-down, right? We want to ensure we choose Enterprise and here choose Sandbox, right? Again, this is all explained here, right? This is just a quick configuration so that it's a more a smaller instance essentially, right? Now for instance ID, we want to use BlockDB, right? We want to name that instance BlockDB, instance ID BlockDB. For the password, we want to type a very safe password, right? Oops, sorry. Just to make sure, very safe password, we're good. Easy to remember. Then we want to choose single zone configuration. Again, that's not the recommended way, the recommended configuration for a production environment, but for our lab, that will be good enough, right? So we want to choose a single zone, right? And set the region and zone assigned by QuickLabs. This is the important section here, right? Where we get to single zone, I choose single zone, and I need to choose a region, right? I need to choose the region that is provided to me in the QuickLabs instructions here, right? In my case, that's US East 4. That might be different for you, right? But you need to make sure you create the instance in the correct region, otherwise it might not be properly recognized by Cloud Skill Boost, right? So here, US East 4, and specify the zone US East 4B, right? Which is the one that I've got set here. And at this point, we are all set and I can click Create Instance. I go down, I had this, and I can click on Create Instance. Now the instance starts being created, right? And at this point, we need to wait a few minutes, 5, 7, 8 minutes potentially, for that instance to be created, right? So now I'll be able to go back to that very first step, right? And continue from here. And when we get to the Cloud SQL, we hopefully the instance will be created, right? So now let's deploy a VM instance and run a web server, right? So we need now to navigate to Compute Engine and VM instances, Compute Engine, VM instances, click on Create Instance. So we create an instance. And here we need to apply a few configurations, right? So first, for the name, we want to set it to blog host. So the name of the instance should be blog host. For region and zone, select the region and zone assigned by Qwiklabs. Same idea, right? US East 4, US East 4B. So US East 4, this is already set for me, and US East 4B. For machine type, accept the default. Perfect. That would be an E2 medium instance. We are all good, right? For boot disk, in the image, we want to choose if the image shown is not Debian Linux 12, right? So at this point, I go down to the boot disk section. And here, this is a Debian Linux 12, right? The bookworm version. In this case, for boot disk, if the image shown is not Debian Linux 12, click Change and select Debian 11. It is Debian 12, we are good to go, right? Leave the default for identity and API access unmodified. So essentially, we don't change the service account that is being used. We use the default service account. For firewall, click Allow HTTP traffic. This is an important step. We need to ensure we click Allow HTTP traffic in firewall, right? Essentially, what it does, it configures this instance with a network tag, and it creates a firewall rule to allow communication on port TCP/80 to communicate from the outside world to our instance, so we can access our website. This is important, otherwise we won't be able to access our website, right? Then click Advanced Options. So I click Advanced Options. Click Management to open the section of the dialog. So I go a bit down, Management. And here I need to go in the Startup Script section, right, to essentially enter this script, right? So here we see automation startup script. We need to copy that text into that startup script box. And essentially we see what it does. It installed with the APT application management tool, the Apache 2 web server, PHP and PHP MySQL capabilities, right? And it starts Apache 2 servers. That will happen whenever our VM starts, right? So we are sure whenever our VM starts, it automatically installs a web server that we can then access, right? All right, leave the remaining settings as their default and click Create. So let's leave everything as is set and click Create. So we create the instance. We see in parallel, we see that the Cloud SQL instance is still being created after about 4 minutes, right? It is still being created. And the blog host VM is being created also, right? So we'll just wait just a few seconds until it's created, and then we'll check our progress button. Let's go. All right. So it's now created. See, we have our blog host instance, right, running in US East 4B, and we can see it has an internal IP address taken from the IP range of the region, the subnet where it is actually running in US East 4, right? And we have an external IP address here, right? So we can check my progress, and we are all set, right? Again, verify that you create your instance in the correct region with the correct name. You follow carefully the instructions. Next step, we want to create a cloud storage bucket, and we'll do this using the gcloud command, right? So in the Google Cloud Console, activate Cloud Shell. So I will activate Cloud Shell here, right? That's the button at the top right, activate Cloud Shell, and it opens the Cloud Shell instance here. So here we click Continue. It is provisioning our Cloud Shell machine, right? Got it. Perfect. And now we can continue, see? And we see the Cloud SQL instance has now been created after about 5 minutes, 5 minutes and a half or something like this. It might take a bit longer for you, it depends a bit. But if it takes anywhere up to 8-10 minutes, don't worry, it will be created eventually. And so here for convenience, let's choose a location, right? Either US, Europe, or Asia, right? So let's choose Europe for me, right? That will be the location of our cloud storage bucket. So we export this as an environment variable, and in the Cloud Shell, we create a bucket, right? G-Cloud Storage buckets create with the location we just stored, and we give it the name of our project ID. Again, remember the name of a cloud storage bucket needs to be globally unique. We use the project ID here, the project ID of our project for the lab, which is also globally unique, right? So we create a bucket with that particular ID. It's perfect. And now if I go to cloud storage, I should see that bucket created. With yes, bucket here. Sorry, that overview is new, right? And we have our bucket with the name of our Quick Labs project ID, right? All right. Now we want to retrieve an image from a publicly accessible cloud storage location, right, into our local machine at this point, right? So we can copy this command. And what it does, it essentially copies that myexcellentblog.png image from a remote cloud storage bucket into our local machine with myexcellentblog, right? So now if I do an ls here, I can see the myexcellentblog image, right? And now we want to upload that local image that we have here to our newly created bucket, right? And we can do this with the gcloud command copy, right? So same idea. We copy that command, and now it copies that myexcellentblog.png onto our bucket, right? Next, we want to modify the access control list of the object. Remember, access control list, right? So we make that object public, right? So we use the gsutil tool this time instead of gcloud. That's a specific tool for interacting with cloud storage, right? And the way it works is we essentially change the access control list to give a user, right, the read access onto all users. And all users is essentially a placeholder for any user, effectively making that object public, right? And we apply that permission, that ACL, to our myexcellentblog.png, right? So if I copy that command here, it applies, it updates the ACL, right? And now if I enter in my bucket here, let's close this, right? And I scroll right a bit, right? I see that this object, myexcellentblog.png, has public access, right? With a specific URL that I could copy and access directly, right? Now I can check my progress, and we are all set. Next, Cloud SQL instance, right? So this is what we've done first to get a bit ahead of time, right? So we run all of these commands up until the click create instance command, right? So now we can continue from there. So now click the name of the instance blockdb to open its details page. So we need at this point here to go back to Cloud SQL. I've got that blockdb instance. I can click on it and I can see the details of that instance, right? From the SQL instance details page, copy the public IP address for your SQL instance to a text editor, right? Because we want to use that external IP address, that public IP address, later on. So this is the IP address we use. We'll actually leave it here. I won't copy it anywhere. I will just open different windows, right? Then we want to add a user, right? Click users on the left-hand side and then add user account. So we want to click on users here, add user account, and we want to add a user, BlogDB user. BlogDB user. We want to set a password for that user also. Very safe password again, just to be sure we remember it, right? And we click add to add the user account in the database. So we can click add. Again, just showing you that I already follow very step-by-step the instructions, right? Everything is really well explained. We want to click Connections menu on the left-hand side and then click Networking tab. So we go to Connections and we go to Networking. We want to click on Add a Network. So add a network here, right? And here, we want to give it a name, right? For web frontend. That's a name for our external connection, right? Because essentially, in Cloud SQL, when you expose an external IP address for your Cloud SQL instance, you want to control who can connect to that external IP address. There are a couple of ways. You can either use an authentication proxy that is very easy to use and manages all of that for you. Otherwise, you need to authorize an external network to connect to that instance. So this is what we do here, right? We want to, for network, we want to type the external IP address of our blog host VM instance. We want to authorize specifically our VM to connect to our Cloud SQL database. Here, what I do is I'll open the compute engine in another tab, right? So here, it expects the external IP of our instance here, right? So I copy the instance, the IP 34.150, and here 34.150.166.171, right? And we want to make sure we add /32, essentially referencing only that IP address, right? You might want to have a look at your CID on ranges for network addresses and IP ranges. If you want to have more details about this, this essentially references only that very specific IP address and not a broader IP range with a set of IPs, right? And so at this point, we can click Done to finish defining the authorized network and click Save to save the configuration changes. Perfect. So it is editing the Cloud SQL instance, right? At this point, if I click on Check My Progress, let's see if it's actually correct or not. It is correct, perfect. Even though it is still editing, perfect. If you see that at this point, it says that it is incorrect, you might want to wait until the editing is actually complete to verify your progress, right? But here we can continue. Now we want to configure an application in our Compute Engine instance to use Cloud SQL, because at this point, we have created our Compute Engine VM. We have started an Apache web server, but we haven't configured anything, right? We haven't set up any web application yet. So this is what we'll do at this point, right? So we go to the Compute Engine VM instance. So I would navigate to Compute Engine here. I've got another tab open myself. And here in the VM instance list, click SSH in the row for your VM blog post. So I want to click on that SSH button for my blog host instance. Then I want to navigate to the root of the web server for the Apache web server, right? That /var/vws/html. So I can change directory cd into that directory, and I'm correctly in that var. Let me zoom in here so you can see a bit better maybe. right? So we are in that var www. Then we want to use the Nano editor. If you prefer to use V, that's up to you, right? This is just a suggestion here to use nano sudo nano index. So we want to create an index.php file within that directory and paste the below content, the content below, into the file, right? This is essentially a HTML markup, right, where we have a specific title, specific information. We'll get back to it in a minute, right? But what we see specifically, let me actually save it here, right? We want to press the commands shown here to save our file, right? So now into the var www.html, I do have an index.php file, right? Essentially, at this point, we do have a web server, right? An HTML page that does include a bit of PHP code that sets the connection to our MySQL instance, right? So we need to provide a few more details so that it knows where to connect in just a minute, right? So at this point, we need to restart the web server, so it takes that new configuration into account. So sudo service apache to restart. Let's restart it. Perfect. And if we open a new web browser and paste the IP address of our blog host VM, followed by /index.php, we should see the information, right? So here, if I click on the IP address itself, again, continue to site, we don't manage SSL certificate. This is the default page, right? But if I do add /index.php, here we do have our own web page, right? Very beautiful page, as we mentioned, right? Very fancy website. Welcome to my excellent blog. And here we see database connection failed, right? With an error specifically, with a specific error. Database connection failed, again, because we haven't specified the database details into that PHP file, right? So when we continue, right? Database connection fail, etc. But to continue, we want to return to our SSH session on Blockhosts and use the Nano text editor to edit the index.php file again, right? So we go back to our page here, we run again sudo nano index.php. And here in the Nano text editor, we want to replace the Cloud SQL IP with the Cloud SQL instance public IP address, right? So here, Cloud SQL IP, we want to replace it with the actual IP of our Cloud SQL database, right? Which is here, if we go back to Cloud SQL, and this is the address, right? So we can copy the address, 34.48. We go back to this section, and now here in DB server, I want to replace that Cloud SQL IP. Make sure you don't mix up the VM IP, the Compute Engine VM IP, and the Cloud SQL IP, right? In the Cloud SQL connection section, we want to enter the IP of the VM. And in the VM configuration here, we want to enter the IP of the Cloud SQL instance, right? And in the Nano text editor, next, we want to replace the database password with the Cloud SQL database password that we used, right? So again, very safe password that I mentioned earlier, right? So now we have the configuration all set, right? So we can save the file again, restart the web server. And at this point, if we return to our database, to our website, and we reload the page, connected successfully, right? So the connection has been established successfully. Now, at this point, again, this is not a fancy website, so we won't do anything with retrieving the data, etc., right? But we see now that the connection has been established successfully to our backend Cloud SQL instance, right? And lastly, to finish with this lab also, we want to configure our application, right, to use the image we have stored in Cloud Storage bucket previously, right? So here we'll go to Cloud Storage buckets. So let's go back here. Cloud Storage. We want to click the bucket that we have created earlier. In this bucket, there is an object called myExcellentBlog, right, that has a public IP. We mentioned it, it's a public access, right, remember. So we want to copy the URL that shows in the public access, right? We want to copy that URL here so we can use it in our application. So copy URL, it has been copied to clipboard. And now we want to return to our SSH session for our blog host VM instance to again edit the index.php file to include that. So we come back here. We are already in the var www.html, right? So we want again to edit our file. So sudo nano index.php. And we want now, right, use the arrow keys to move the cursor to the line that contains the H1 element, right? So this is this element here, right? H1, welcome to my excellent post, right? And we want to put a new line here, right? And at this point, we want to essentially display an image that will use the URL of our image in cloud storage, right? So we need to enter this tag, right? This HTML tag. So img source equal opening tick, and then we paste the URL of our website, of our the URL of our object in cloud storage, right? The full URL that we have here that appears as storage.googleapis.com with the name of our bucket. Remember, don't put sensitive information, and the name of our object, and we want to close that with that tick and the closing tab, right? At this point, we save the file, we restart the web server. That's shown here, right? We restart the web server, and if we return to our blog host instance and we refresh, we now see that very beautiful image again, right? But we have that image downloaded from Cloud Storage, and that connection successful to Cloud SQL, right? And this is it for our lab, right? But again, pretty complete lab that does illustrate essentially how easy it is to run your application. Again, here we take the example of Compute Engine. We run our web server on a Compute Engine instance. We could perfectly run it on another compute solution on Google Cloud. That could be on our Kubernetes clusters, that could be on App Engine, on Cloud Run, on Cloud Function that we'll see later on, etc. We could even use it outside of Google Cloud. We could run our application outside of Google Cloud and still access Cloud Storage, Cloud SQL, etc. Right? But at this point, we have finished our lab, so we can click on End Lab again. Right? And again, I took some liberty, right, to run the Cloud SQL first. So essentially, I took about half an hour to run the lab, right? Don't worry if you take more. Feel free to read carefully all the instructions. Take your time. You will have an hour and 15 minutes to run the lab, right? But I can click now on End Lab, and I am all set. All right. So this is the lab for our storage section, right? So I will now close all those remaining pages, right? And we are all set. Remember, when you click on End Lab, this actually under the hood destroys the Cloud Storage buckets, the Cloud Storage, the Cloud project, right? The entire project, including all the resources that are in that project. It will destroy our VM, our Cloud SQL database, our cloud storage bucket, eventually destroys everything, right? Remember also that you can run each lab up to 3 times only, right? Whenever the lab times out or you click on end lab, it counts as 1 run. And you can run each of those labs up to 3 times, right? But this is the lab for our storage module, right? So again, we could have played also with Cloud Spanner, with Bigtable, with Firestore, right? Here we just wanted to illustrate cloud storage buckets and Cloud SQL database, right? We'll be able now to continue with our next module on containers specifically, right? So let me actually bring the next module on screen, right? And perfect. Containers in the cloud, right? We'll cover a bit of history, a bit of details on how did we get to containers, right? And we'll cover more specifically Kubernetes and Kubernetes Engine. So one thing to note, Kubernetes Engine, this is a whole world in itself, right? We do have a number of courses where we spent 3 entire days talking about Kubernetes, and we are still missing some time to get all the details on Kubernetes, right? We could have an entire week of course regarding only Kubernetes specifically. This is kind of a beast in itself, so this will be a short introduction into Kubernetes, right? But before we start with Kubernetes, let's talk a bit about containers, right? Containers, how did we get to containers, right? If you remember from our first module, we talked a bit about how did we get to the cloud as it is nowadays, right? So we mentioned first the historical IT approach, right, where organization would manage their IT on their own servers, etc. Then we mentioned co-location, where a third-party organization takes care of managing the real estate, the data center building itself, the connectivity, the supply for that data center, and organization bring their own hardware. Then we talked about virtual machines, right? And virtual machines, they are still very widely used, obviously, right? Compute engine virtual machine, right? This is really the backbone of infrastructure as a service solution, right? And virtual machines, they are really useful to use the underlying resources from the physical hardware in a very efficient way. Which provides the ability to run different computers onto the same physical host under the hood, right? The way it does that, it essentially, instead of installing directly an operating system on top of your underlying host machine, as you would do with your computer, etc., as it was done previously, right? Instead of installing an operating system that would be aware of all the resources of that underlying server, we now install a small piece of software that's called a hypervisor that will act as the interface between the underlying hardware and the underlying resources that that hardware comes with, right? CPUs, memory, disk storage, network connectivity, right? And the computers that will now be able to run on that underlying machine. So now the idea with virtual machines is that you will be able to create several VMs, several computers onto the same underlying host, and provision, give access to a limited amount of resources on the host to each virtual machine. which does provide the isolation between those, right? So, for example, let's say you have an underlying host machine that does come with, let's say, 10 CPUs and 20 gigs of memory, right? Typically, when you install an operating system directly on that machine, the operating system will be aware of the 10 CPUs and 20 gigs of memory. Now, if we install that hypervisor and start running virtual machines, we will end up having different machines that we can configure. For example, one of the virtual machines to have access to 2 CPUs and 5 gigs of memory, another machine to have access to 4 CPUs and another amount of memory, etc. Right? So this is typically something we want to control to limit the amount of resources a given machine can actually access, right? And this also brings us the ability to configure those machines, those virtual machines differently, right? This allows us to, for example, run the first virtual machine with a Linux distribution, the second virtual machine with another distribution of Linux, run our next virtual machine with a Windows operating system, etc. Right? So this is typically how virtual machines work, right? And they do provide the ability to get much more detail how we want to configure this, right? Let me actually show you a bit of a short image on this, right? Let me actually show you here. If you just bear with me 1 second. Okay. And let me see. Right, now let me go here instead. Just 1 second, so I can just show you a much better picture. Is going to be much more convenient for that matter. All right, let's go here. Let's go here. Perfect. And here. And let me actually paste it here instead, right? So up. Containers in the cloud, as I mentioned, right? And so this is a bit how virtual machines are a bit configured, right? We do have under the hood that underlying hardware, which comes again, as we mentioned, with storage disk, with CPU, with memory, with networking capability, right? But we don't install our operating system right away on top of it. We do run a hypervisor layer. That hypervisor is a software layer that is in charge of interfacing the virtual machines we will start on that underlying host with the resources it brings, right? But this allows us to, for example, grant, let's say we have 10 CPUs in that machine and 20 gigs of memory. We can give each of those VM 2 CPUs and 4 gigabytes of memory. We could potentially have bigger VMs than others, etc. Right? But as long as we have enough resources on the underlying machine, we can create as many VMs as we want, right? And those VMs, they are limited to the amount of resources that we configured them with, right? In this case, for example, they won't be able to access more than 2 CPUs and more than 4 gigs of memory. They could potentially, there are different ways, right? But by default, they would be isolated, which means that already we can run different applications, each one on their own virtual machine. And we are sure that those applications won't use more resources than they should, right? If we were running those 5 applications onto one single operating system instead of a hypervisor on that machine, typically, historically, there was no way to limit what resources could an application use. So at some point, you could have a web application server and a database application running on the same host machine, and potentially at some point, the web server receives more requests, it starts using more CPU and more memory, and it started starving the other applications running on the same machine from the resources they need, right? With virtual machines, we provided the isolation between those applications. Now, each application, a web application server, our database, etc., they could have their own virtual machine, their own isolated environment with, for example, 2 CPUs and 4 gigs of memory each in our case, right? Our web application server could have a specific Linux distribution operating system that actually fits its needs best, right? And the specific configuration needed by that application specifically, right? Our database application could run a Windows operating system and a specific configuration to fit its needs, etc. Right? So it provided isolation for each of those. And then as long as we have enough resources available on the VM, on the underlying hosts, we can run as many VMs that fit in that particular host, right? At some point, typically, for example, that web application server, right? Let's say it starts receiving more requests. And at some point, one instance provided with 2 CPUs and 4 gigs of memory becomes saturated with that number of resources, with that number of requests, right? It would not be able to respond to more requests. Here we would have two options. Potentially, if there is some room and more resources available on the underlying machine, we could potentially resize this VM and provide it with 4 CPUs and 8 gigs of memory or more. This is one option, but the VM approach to handle such situation would be to create a replica of that VM. Essentially an entirely new replica, exact replica of that VM configuration, etc., and run it in parallel, right? If there is some room on that same underlying machine, we can run that VM on that same machine. Again, that would be the exact same configuration, so another 2 CPUs and another 4 gigs of memory. If there is not enough room on that underlying machine, we can just start that second VM on another host that has a compatible hypervisor, and it would then run on that other host machine, right? But we would have 2 replicas of our VM. Then obviously, as we saw earlier, we need a load balancer, right, to balance the load between those different VMs. So that would be the VM approach. The VM approach that have been widely used now for a couple of decades or more for a very convenient usage of the underlying resources, right? We can fit as many different type of VMs with different configuration on one single piece of hardware. Previously, we needed to install an operating system with a very specific configuration that might not fit different type of applications, right? And now with VMs, we do have this option. The thing with VM and the limitation with VM when it comes to scalability is that, as we see here, every virtual machine comes with its own operating system, its own full-fledged operating system, its own kernel, its own user space, full-fledged operating system, right? And typically operating systems are notoriously pretty big pieces of software and pretty slow to start.
It's 11:38 a.m. It's 11:45 a.m.